So hello, my name is Jalal. I'm a technical architect at Ubisoft Montreal. I'll be talking today about some of the architectural optimization we did on Rainbow Six Siege. So of course, the work I'm presenting today is the work of the whole 3D team. So I'd like to thank them in this slide. So I will start by giving an overview of some of the rendering passes we're doing on Rainbow. Then I'm going to talk about two of my babies on this production, which is the material-based draw cause system and the checkerboard rendering. So the rendering overview. So what is Rainbow Six Siege first? So it's the rebirth of a very loud franchise. So that meant that a lot of hardcore players were waiting for the game, and for the hardcore players, 60 FPS on competitive gameplay is really important. So it was really important for us to hit that target. Also, we had to give more importance to the PC build, since a lot of hardcore players actually play on PCs. Also, we have a gameplay-driven game. So if you have to do a trade-off between graphic beautifulness or animation beauty, we're pretty much going to always go for gameplay and something that's going to improve the gameplay and the user experience of the player. So we also have the destruction as a core gameplay mechanic. So, and destruction needs to be pretty much consistent between all platforms. So since in competitive mode, you don't want a low-end PC to have different outcome than a high-end PC, so most of the destruction needs to be equivalent. Also was the first rendered that ships, it was the first Rainbow Six that ships with the engine, and we had a lot of legacy code. So Rainbow Six had a lot of development through the years, a lot of PS3 specific code that needs to be cleaned up. So we had to survive a lot of legacy code. A little video in reverse that I just pulled off of the internet, showing what we achieved. In reverse because it's cooler. Yeah. So on the tech side, so we were targeting 60 FPS. That meant that we need to run the GPU at 14 milliseconds on average on non-combat situations. And we also negotiated with the engine team at 38 millisecond linear on CPU. And our critical path was around 10 milliseconds on average. Also needed to provide scalable destruction, which is important, since you want when a level starts to start at 60 FPS, and also when it ends, when there's been a lot of combat and a lot of stuff happening on the level, to still be at 60 FPS. We also wanted to ship at a resolution bigger than 720p on all platforms, and we wanted to commit for 4K on PC. So also to support a wide range of PCs, so we need to support 1 gig video graphic card. And it turns out to be quite difficult when you target current gen, since if there's one thing that we have, I think, plenty of on the current gen is actually memory. So yeah, that needed a lot of work to pretty much get back all the default cost of the engine to be able to run it on 1 gig graphic cards. So one more thing, that Siege is a live game, so we're still doing updates. We're still working on some graphic features. We're still doing development. One of the stuff we're looking at is auto exposure. A lot of players are complaining of visibility from inside to outside, and it's stuff that we're still looking for. And we have to be careful not to break things. Just a couple of weeks ago, we released an update where some shaders were missing, and we ended up with this bug on screen. So. Here's a hierarchical view of a GPU frame on Rainbow Six Siege. So we spent on average 5 milliseconds on geometry rendering. So to achieve that, we rely heavily on Culling. It's going to be the draw call-based material system that I'm going to be talking about in the second part. And we also do a lot of shadow caching. We spend also on average 5 milliseconds on lighting. We do screen space reflection, and this actually also includes screen space reflection pass, not the ray tracing, because it's done on async in parallel of shadows. Here is where the checkerboard rendering technique, which is going to be the second part of the talk, helps the most. And we also spend an average like 4 milliseconds on various post-processing, like downscaling hierarchical Z-buffers and stuff like that. On CPU, our critical path was around 10 milliseconds. And we implemented the Ascader where actually most of the rendering passes can be automatically independent on the number of draw calls that we're going to do, going to be split up in smaller pieces. So even the opaque, pretty much, if we know that it's going to take around 4 milliseconds, we're going to automatically split it in different pieces. And we're going to try to maximize the number of command buffer execution by having the graphic thread, which is our immediate context thread, steal tasks in order. And so pretty much like visibility in all other passes like gets stolen, and we don't have any overhead on that. We're able to still squeeze the most out of our main graphic thread. Also, like shadow caching helps here a lot. I'm going to be talking more about shadow caching. We, like I was saying, 4 milliseconds. Actually, like currently, the 4 milliseconds is spent on the opaque pass, and we rarely like go above 4 milliseconds, even like with the number of draw calls we're doing, virtual draw calls. So, for example, like one of our passes. So I'm going to be repeating Culling and high Z a lot in this talk because pretty much we do high Z Culling in every single pass on our renderer. For first-person rendering, we pretty much start by rendering the first-person character to the G-buffer and depth buffer. From that, we just render the first 100 best occluder that we have on our scene, which is usually just the 400 closest objects to the camera, to the depth buffer. We downscale that depth buffer to generate a high Z buffer, starting from 512 to 156. And we use that hierarchical Z buffer to actually perform culling on the subsequent passes that uses the main view, and most notably the opaque pass by itself. So for shadows, all shadows pretty much start off with a cache. And we always, when doing caching, we generate a hierarchical Z buffer from that cache to perform culling. For the resolution part of the shadows, we do it on a separate pass. Pretty much we had it in the beginning merged with our lighting resolve, but the VGPR pressure was too big, so we just moved it from the lighting resolve. And also use the hierarchical Z buffer of the shadow map to pretty much determine if a whole block is shadowed or not and skip work. For local light, we just resolve them in quarter res. Turns out to be like a good quality versus performance trade-off. So for shadow maps, we always start when loading a level by shooting a static shadow map, which is 6K by 6K, 16-bit. We do it at load time, not at map generation time, because we have a lot of gameplays where actually level designer place objects that are randomly going to appear and block some passages, block some windows. And those actually are very good occluders that we want to get into the static shadow map. And most of the time, like 99% of the time, they are static objects. So it's actually better to have them on the static shadow map. So from that, we generate a 512 by 512 ESM that's going to be used for mainly large particle shadowing, and also generate the hierarchical Z buffer. So to scale our shadow rendering, we blend between the static shadow map that we generated at map load and dynamic cascades. So, and all the dynamic cascades are going to actually use the static shadow map to do culling. So like on consoles, Xbox One, for example, the first cascade is fully dynamic. because we don't have enough resolution with 6K to actually provide good enough quality. The second and third cascade contain just the dynamic object. And when we render those dynamic objects, we use the static the static high Z buffer to actually do culling and reduce the amount of draw calls and the cost of doing the rendering of dynamic parts. And we just blend between the static and the dynamic shadow map. The fourth cascade is pretty much substituted by the static shadow map. And we have the ability pretty much to scale that dynamically, or like on low-end PC, we just generate one dynamic cascade, and everything else is the static shadow map, etc. Because we have a lot of local lights, like usually a level have like more than 80 shadow spotlights, we can't have them all in cache at any given point. It would cost too much in memory. So what we do is when we encounter a new light, and we actually only support a maximum of 8 shadow lights on the frustum. So we encounter a new light, we always shoot the static part of the shadow map. When we shoot the static part, we generate a hierarchical Z buffer from it. Then when we render in the light, we just, instead of clearing the depth buffer, we just copy the static part into the dynamic part. We render the dynamic objects on top, and of course, we do culling, since we already have a hierarchical Z buffer. And then the result resides in an array that can be accessed in further passes. So for the lighting, our lighting is based on clustered structure. Each frog cell is 32 by 32 pixel based and has a Z exponential distribution. And we also perform hierarchical culling on the light volume using the high Z, the view high Z buffer and other, like just going through the structure hierarchically. And we fill each cell with the list of light that we're going to render on that cell. And we also see local cube maps as light. So they are gathered within the light list volume. And just like when we render them, like they're pulled off the same way. We just maintain an index, and they actually reside in a cube map array. The same thing we do for shadows and gobos. So pretty much everything is in arrays, and we only maintain indices in that array. And during the rendering, we just need to fetch the shadow or the cube map for a given cell. So that allows us to pretty much handle the same features between the forward and the deferred pass. So I'm going to be switching to the second part of the talk, which is the material-based draw call system. So Rainbow Six destruction, we had like a main guideline from the art direction, which was when destruction happens, it really needs to be visible. So when you go into a room, you didn't see destruction happening, you just see the aftermath of it. You need to know that there has been like a big change. So we need to pretty much have better persistency of objects, and have this feeling of a lot of volume getting generated from destruction. Fortunately, we're dealing with a close quarter game, so we have walls and floors mainly to destroy procedurally. They generate a unique geometry. Problem that we have with that is that they're usually very good occluders, but not in our case. When you start poking holes into walls and floors, like you lose occlusion efficiency. We also have to deal with a lot of debris and props. So those are usually smaller meshes, but they are in greater numbers. Can also be procedurally generated, so they have unique geometry or instanced. So here's an example of a destruction. So I'm going to decompose that. So in our game, it's really important to have like the player model the destruction the way he wants. So if he wants to shoot a wall that's a hole that's like just 2 centimeters from the door frame, he can do so. So we generate a lot of unique geometry for that, and to pretty much have this like volume that's getting conserved from the hole in the first place, we generate a lot of debris to fill up like the space beyond the player. Like in this situation, we have more than 100 debris that got generated from the destruction. Some of them are going to disappear, but most of them are going to stay persistent during the whole actually round, which can last up to 3 minutes or even more on PvE games. For the occlusion efficiency, so I took a wall and shot a couple of bullets into it. So you can see how pretty much those holes are going to propagate along the hierarchical Z-buffer, and thus making like an object that's small enough on screen, but we're going to pretty much select this high Z level, the high Z texture level, to do the A/B test, and we're going to actually pass it as visible. Even though it was tested like on a bigger level, it would have failed the test. So pretty much easily reduce our occlusion efficiency just by poking a couple of holes in any given wall. And that happens a lot in gameplay, actually. So the early prototypes were largely graphic, CPU and GPU bound. Like once we go through computing the destruction by itself, we have to render it, so there's all the debris that get generated, all the unique geometry that gets added into the world. So we started thinking about ways on improving that. And of course, our first implementation only had a PC, DirectX 11 deferred context style of render, which is not great at scaling. So we thought of like what we have pretty much on our scenes, and you can see that when you do a destruction, usually a lot of stuff share the same material. So most of the debris that are going to be generated share the same material. Walls usually also share the same material. It also goes from like this art direction where destruction have to be like visualized by the player. So if like we use in a red wall, it means that can be destroyed. So it's a lot of red walls here and there. So we can actually batch a lot of stuff by material by design. And as I said, all the debris share the same material, which helps. There has been a presentation, because we're sharing a lot of work with Assassin's Creed Unity done by Ulrich Haar last year. That's interesting. Like there's stuff that I'm not covering, but actually they are covering. And I'll invite you to go see it. Also, we wanted more granularity in culling, since when we decrease like the efficiency of our culling, we want smaller unit to actually be able to select a higher level MIP in our high Z buffer to do the culling. So to implement that, we started off by unifying a lot of buffers that we have on our renderer. So in Rainbow Six, a lot of resources will reside in some unified buffer of some sort. So we have the unified vertex buffer, which is like one buffer that contains the geometry for the whole map. A unified index buffer, same thing. Unified constant buffer, it contains all the context, all the constants for the whole draw call. So we pretty much simulate structured buffers on top of that. They're implemented as byte address buffers, but we generate some C++ code to help access it from the CPU and from the and some HLSL code to help access it from the GPU. We also add some metadata to pretty much explain how we're going to access this data to do it more efficiently. So here's an example of how we generate that code. So we go from a descriptor that is in C++ that pretty much just goes through the different values that we're going to pass on to the GPU, like we declare them. We generate an equivalent HLSL code that's going to help us load that chunk of data from a unified constant buffer. So all the draw calls are going to be used and bind just this buffer, and we're going to use indices that we pass along with our pipeline to be able to fetch those values. So what's cool about that is that we have complete control over data layout. So we can easily like We tested a lot of stuff, like structured of U32 arrays, and just a couple of lines actually in our code to change from one method of access to another, like AOS, SOA. It can also support in constant buffers other type of data and be pretty much going to be hidden from the high-level programmer. We can have like RGBA8 or other type of format, and it's just going to be transparent because we generate all the code that does that. And to some certain extent, and especially on GCN, anyways, those are instructions that do the same thing, so better just do it ourselves. So we also support some high-level APIs to be able to broadcast values into different constants. So since all the copies and all the management of those buffers we handle ourselves using compute shaders, we can pretty much do broadcasting values quite easily. And code generation is always nice on iteration, and to migrate access pattern, to do tests, and to pretty much do whatever we want with our data and give us more control on our render. So, as I said, so the geometry, which is the unified vertex buffer, unified index buffer, and constant are unified in our render. So a draw call is going to be defined by the shader it uses, the non-unified resources like textures, and the render state like sampler state, raster state, etc. So elements that are going to share all of the above are going to be batched together. And all the passes that actually just going to use a subset of the different non-unified resources, like in a shadow pass, we're just going to, if you don't have alpha testing, we're just going to skip fetching the textures. We just like remove them into our batching computation. So when we initialize our render or when we load a map, so each submesh instance is going to be mapped to 3 types of batches that are going to be used like all through the rendering, which is the normal, shadow, and visibility. So those kind of like types just are a helper to mask different type of data and try to remove some of the stuff that is not used in any given pass to increase the amount of batching. And each one of this batch in the end, when doing the rendering, is going to correspond to a multi-draw index indirect command. So here I have an example of 3 submesh instances. So each one of them is going to map to a different normal batch. 2 of them are going to share the same visibility batch, and they're going to be drawn with the same multi-draw index indirect command. And the instance 2 is going to have its own visibility batch. And then the 3 of them are going to share the shadow batch, which is usually the case. Like shadows are more batchable by design. So, and then on the GPU, to pretty much access the data for each of those submesh instances, we maintain a globally unique index all through our pipeline that is maintained by the GPU and help us fetch any kind of data for a submesh instance. So from that index, we can go to multiple level of indirection to fetch like the vertices that are going to be used when running the vertex shader, the transform matrix. So just like depending on the data that we want to fetch and its frequency of access, you're going to have different index, and it enables us to fetch whatever we want. What's important to note is that sometimes we take one level of indirection off just to speed up the access because we don't want to do too much indirect accesses to some of the like further laid out data. So for each pass that we do, like the opaque pass, what we start is gathering in a dynamic buffer all those globally unique indices. So each pass is going to map only to one batch type, like normal, shadows, or visibility. And takes us around 1.5 milliseconds to gather all of those indices for all the passes. So we just like spawn jobs at the beginning of the frame. We gather all those indices, and then we start rendering using the dynamic buffers. We also append some extra data that can change between frames. And we also write our offset into the dynamic index buffer that we're going to be building when we're going to do the advanced culling per triangle. So from this path buffer that contains the list of all the submeshes for a given path, we start by doing submesh instance culling, which is like culling per that frequency. It's either we're going to draw the object, it's going to go either directly to the draw path, or it's going to be further culled, or we're just going to discard it from the start. So if it goes further down the culling path, so all of our meshes are split in chunks of 64 triangles. We do culling for those 64 triangles. And if the chunk passes this phase, we do backface culling per triangle. And in the end, we only draw pretty much the triangles that passed all of those culling levels. So on the first level of culling, which is like per submesh instance, we start by screen space size culling. Then we do distance culling, frustum culling, occlusion culling. So our renderer actually starts by doing like a very coarse culling phase, which gathers a bulk of objects. And then we just go through them and further cull them, can actually discard a lot of stuff on the frustum culling pass too. The second level of culling, which is by 64 triangle chunk of each one of those meshes that passed the first level of culling. We're going to pretty much go through the same thing. We substitute the distance culling by orientation culling. So in a baking phase, we just try to compute a normalness spread for each chunk, and we do orientation culling at that stage, and then we do occlusion culling. So occlusion culling on that stage enables us to improve our culling efficiency, since we reduced the size of any given object we're going to cull to chunks of 64 triangles, so we have better chances to fetch the Z samples from a higher level MIP on the high Z buffers. Then if everything passes, we do just triangle normal culling. We maintain a buffer active for each triangle, and we don't fetch the vertices. And we have a buffer with per triangle normals that we fetch and do the triangle normal culling. So we go from this path buffer, we do all this type of culling. Then we're going to fill up a multi-draw parameter buffer. And for each batch, it's going to be multi-draw indirect with all the parameters laid out. So, and then on the draw call itself, what we do is we start from the start instance that we fill out during the culling to fetch the submesh instance index, which actually the start instance is directly the submesh instance index. And that is used to fetch the unified constant buffer for that instance, which is going to help us through an indirection get the mesh descriptor. And using the start index, which is SV vertex ID, and the dynamic index buffer and the unified vertex buffer, we're going to fetch the vertex data. So in the end, like, we run our vertex shader and we fetch all of the data ourselves. Yeah. So vertex shader is going to pretty much consist with this of this fixed input, which is the per instance primitive info that we're going to just fill out with the global instance index of each submesh, and then the hardware generated vertex ID. And then we already generated the code to actually fetch from the global buffer using those indices, the vertex info by itself. Then to pass on the data from the vertex shader to the pixel shader, since we don't want per pixel to actually fetch all the indirections, we pack up all the resultant indices that are going to help us like get any kind of info used in the vertex shader in a non-interpolated attribute passed on from the vertex shader to the pixel shader. And what's important to note, which is a good optimization, is actually use read first lane on that value, since you want everything in there to be in the scalar registers. We got pretty good wins on Xbox One and PS4 by using that. So here an example of like doing destruction and amount of draw calls added to the scene. So just took walls that similar in material, shot a couple of explosive into them, and we just added 5 draw calls compared to the original scene that we were drawing. So batch visualization, pretty much that shows you the color coding of the batch. You can see all the debris sharing the same batch. Also, the decals that are drawn on top of the debris are also using the same pipeline. We have some tricks to actually do sorting per batch level on them, and we pretty much impose some constraints on the artists on the number of levels that they can have on their decals. And actually, the sorting of the decals is kind of fixed, so they have to choose from the beginning that you're always going to have decal like type 1 on top of decal type 2, whatever happens. So for this scene, for example, we go from 10,500 draw calls. Like those are draw calls that we would do if we didn't have the whole system. So they correspond actually to the submesh instance, the submesh instances that we're going to draw on the scene in the end. From that, we end up with 412 batch draw calls for the opaque, decals, and visibility pass. Visibility pass is usually on our render just 6, I think, to 8 draw calls on average, like something like really ridiculous. And 64 draw calls for the shadows. And from beginning to start, we managed to drop off 73% of all the triangles that were originally on the scene, knowing that we already do coarse culling on CPU to start up. So what problem that we shipped with, and we're working actually to improve in future updates, is that we push in a lot of empty draw calls. Empty draw calls have a cost. So just like the command buffer running on those empty commands is going to take time, and it's time that the GPU is doing nothing. We try to hide it with async jobs, but it's not enough. It's actually, if the GPU can manage to work, it's better to do work. So the next thing is pretty much just be able to specify the final number of draw calls on the GPU. And when we know that we called on the GPU like 10 out of 20 draw calls, we're just gonna do an issue those 10 draw calls instead of issuing the whole 20 draw calls and have some of them with 0 indices. We can pretty much move to bindless resources to improve the batching. We still don't see the benefits right now for it, but can help us also reduce even furthermore the load on the CPU. And we want to move all the traversal of our scene graph to the LOD. Pretty much have all the scene being descripted on GPU. The CPU doesn't know pretty much anything about it. Right now, we have very complex CPU code that does LOD selection. We're moving it to the GPU, and then we're going to do LOD selection on the GPU, and everything's going to go without any CPU intervention. So the last part of the talk, which is checkerboard rendering. So for us, as I said, 60 FPS was important for adversarial PvP games. So we wanted to target it early on in production. So we were working hard, like pretty much to reach it. Like in our first playable, we managed to have around 50 FPS. A couple of weeks later, we were at 60 FPS, and afterwards, we're just like pushed to maintain that frame rate. So anything that goes in the engine or in the art have to be performance approved. And to be able to have like a quick jump on the frame rate, we started thinking out of the box. Like Killzone came out when we were like pretty much working on those techniques. And one interesting thing that they were doing is pretty much rendering half the pixels on screen on their adversarial games. They keep the same cost per pixel as a 30 FPS game, but their technique was EQA based. And we wanted our stuff to run on PC too, since we wanted really to have like the best performance possible on low-end PC and have decent frame rate with decent GPU on 4K. Was a big quick win for us. We just enabled it like without telling anyone on the floor that what has been enabled, just to see if people will notice like any quality drop. Luckily, people noticed like just the increase in frame rate, which is good. So what we implemented was pretty much, instead of rendering to 1080p render target, we reduced the resolution on the y-axis to 960 by 1080. We maintain a velocity vector per pixel, which is 3D. And we have R12, G12, B8 format that you're going to have pretty much the implementation of it on the bonus lab if you're interested. Then each frame, we just offset the projection matrix to render either the even or the odd lines. And one important thing to note is that to get correct texture gradients, you need to fix them up. Since the scaling is not uniform between the two axes, we need to divide the DDX by 2 when doing the sampling. So we need to go through all our shaders and fix them up depending on what they're doing on screen. So, of course, things that are not represented by motion need to be dealt with. So lighting changes, shadow changes, transparency. We started like doing a lot of like work to maintain a history buffer just of lighting and shadows and try to determine if for a given missing pixel there has been like a change just on either of those to better fill that missing pixel. It was taking like too much actually GPU time and too much memory, additional memory that we have to maintain between frame. We end up pretty much just relying on color clamping most of the time, as explained in the Unreal TAA paper. Also, a lot of data needed to be tweaked. Artists like to do very sudden effects, and usually those effects are the ones that are not represented in the with velocities. Like they're going to do like one frame flashes, particles that are going to change per frame. So you can have that if you want to have decent quality. So a lot of stuff needed to pretty much be tweaked to have like a less harsh transition. And all our like engine oscillators, we just hack them to never have a 0 to 1 transition. It always go through a smoother curve. Still had a lot of issue with aliasing on vertical lines, and like fixing that wasn't easy after all, and took us I think a couple of months to get to something working properly. But we were not satisfied with the aliasing properties of the technique we chose. So this is where checkerboard rendering comes. So the base idea was to actually solve the aliasing issues. We experimented on a series of images and compared the signal to noise ratio, and it was usually better if we were using checkerboard pattern to interpolate between the missing pixels. So the idea of using MSAA to X like was bouncing around since the beginning, and we made a push for it for E3 2015, and in 2 weeks we switched to the technique that I'm going to describe right now. So here is a couple of examples. So we took some images, took off the vertical lines, the odd vertical lines, and we reconstruct the image from the neighbors, the direct neighbors of each pixel. So you can see line versus checkerboard. Like there's less visible aliasing on the image. Sorry about the noir. The resolution of those screens are not high enough to display the image properly. So other example, checkerboard versus line, less aliasing. Like on a computer-generated image, less aliasing. Oh, sorry, this is actually shows the def. So how do we manage that? So we start by rendering to a quart-res render target. This quart-res render target is going to be MSAA to X. So quart-res multiplied by 2, half the pixels, pretty much ends up being the same amount of pixels as the full the previous technique. So we just use the standard MSAA pattern, which has 2 color and Z samples, which is perfect. We want this thing to run on PC, and that works on PC. And we just need to run our pixel shaders per sample instead of per pixel, because we still want the frequency of shading to happen on each of those samples we are rendering. So in the end, each of those samples is going to line up exactly with 1 pixel on the final render target. So checkerboard rendering. The good thing that we get with that is that on our particles, we can just, instead of evaluating the pixel shader per sample, can do it per pixel. We do that for smoke and other effects. So we don't have to deal with sorting between like small particle buffers and normal particles. Everything that needs to go full quart-res, it's just going to be evaluated per pixel instead of per sample. Also, we can fit a lot more stuff on the ESRAM. So all of our render targets are actually half the size, which is good. And we don't need to fix up the gradients anymore. Why? Because right now, the scaling becomes uniform. So instead of dividing the dx, dy, which actually costs some ALU, we just bias the MIPS by 1, and we have the same result. So instead of being some cost that we do on the GPU, it just, like all of our samplers, change the MIP bias when we switch on this technique. Actually, this technique can be switched on and off on PC. So consoles give you the control of choosing your sample locations. It's not possible on all GPUs on PCs. I think it's only on Maxwell on NVIDIA. But it has been there for a long time on AMD, actually. So to unify our implementation, instead of switching the sample location, we just offset the same way we were doing before between 2 frames. So it's going to yield the same result, but we're going to end up with one missing line that we have to do proper clamping when you actually fetch the values. So to reconstruct the missing pixels, which are represented here by P and Q, we sample the current frame direct neighbor, which are in linear Z. We sample the linear Z direct neighbors. We also sample the direct neighbors colors for each missing pixel. And also we compute history color. There's a C missing, and Z. So to compute this history color, we're going to select one of the direct neighbors' velocity to do reprojection. So we tested a couple of stuff. We ended up just choosing the closest one to the camera, since we always want to preserve the first-person object on screen, and you don't want a silhouette to be mixed up with other stuff. So we chose the closest pixel, like currently rendered pixel to the camera. And with that motion velocity, we sampled the previously resolved color, so the full resolution render target. So we use bilinear filtering. And actually, I think we need to try to to use cat-mirror interpolation. So I heard it's going to yield better results. But that can introduce accumulation color. We didn't see that much effect on our rendering, but it's a possibility that we didn't actually run into. And then we clamped the reprojected color, that's history color we computed to to the neighbors, direct neighbors, like for Q it's ABEF. And then using the previous depth, because we maintain a 3D velocity vector, we determine if the pixel was hidden next frame, and we blend back between the unclamped and clamped value dependent on how sure are we of that pixel being hidden or included in the previous frame. So now having this history color and the interpolated direct neighbors, the interpolated color from direct neighbors, we define a weight that we're going to use to blend between the two. Since, like usually when you have transparency, when you have lighting changes, it's always, or most of the time, it's better to just use the interpolated color instead of the reprojected color. It's going to yield like better results on the image. So depending on the minimum difference that we have between those neighbors, we're going to define a weight, and we combine it with different weight depending on the magnitude of the velocity. So the bigger the velocity, the more we're going to tend toward the interpolated color instead of the clamped color, history color. And yeah, we using those two weights, we just write out the final color. So here, like I'm not going to explain this diagram, just like to show you like the complete pipeline that we go through to determine this this missing color. Is actually a lot of passes and a lot of determinations, and we have a lot of knobs to either have more ghosting or more flickering, depending on the situation on the map. So the resolve is quite complex, and we did a lot of tweaks to get it right for our rendering. It runs in full res and costs about 1.4 milliseconds on Xbox One, and we have a net win of 8 to 10 milliseconds each frame. So on top of that, we run TAA. So it integrates well with checkerboard renderings. It's already like doing the whole clamping and velocity vector reprojection, and actually it can run on the same shader, but we separated just also for VGPR usage. So it's kind of like, imagine that our pixel is actually one of our samples. So per sub-sample level, we have this flipboard MSAA RX style jitter that we're going to just flip through each frame. So we have a total cycle of 8 frames to determine like the final color of one pixel. And the reprojected color uses similar weighting logic that we use for determining the missing pixels. And on top of that, we run this untethening algorithm to smooth out some of the imperfection that we have when we're doing the resolve. So because during the resolve, we're going to interleave perfect pixels that were rendered this frame we're sure about to imperfect pixels that were projected and that went to a lot of like history. So we apply a filter to detect patterns that we might introduce when doing the resolve. So that detector filter is going to run on 5 horizontal and vertical adjacent pixels. We determine a threshold, and depending on that threshold, and if each of the 5 pixels either are above or under that threshold, we generate a mask of either 0, 1, 0, 1, 0, or 1, 0, 0, 1, 0, 1, anyway. And we detect that pretty much we have this teething pattern on screen. And if that's the case, we just blend more between the different samples to try to remove it. So it's more blurriness, but it's for better image quality in the end. So the overall technique was like very good for us. We managed to get a lot of GPU time out of it. Similar quality, like it's close enough to that, like for us 3D programmers, of course, we're going to see that there is something being done on the image, but for the average user, and it just like means better frame rates, which is what we were targeting. And it's really interesting when you want to target 4K, because instead of like having this 4 times resolution scaling, it's just 2 times. The implementation wasn't very scientific. It was pretty much trial and error, just testing stuff, seeing if it looks better on our game. So maybe we need to define a better framework for what we did and have more scientific approach of whatever weights we choose to have in the technique. And pretty much we're still gonna like run with it, even if we have like better GPUs or whatever, just because it allows us to actually push the quality per pixel, which is interesting. So special thanks to all those guys that helped on the presentation and also for the insights on the techniques. Thank you, guys. Questions?
Hey, great talk.
Thank you.
From playing Rainbow Six, I noticed there's no motion blur in the game. Is that because of the checkerboard pattern?
It was actually a choice, the art direction choice, not to have motion blur. And the technique actually, and TAA by itself, introduces this kind of like blurring on the image that I think was enough blurring for what we had. So it was kind of like an art direction choice not to have motion blur. But it actually makes sense to have motion blur, since it's going to help smooth out the results and lessen any artifact you might have from implementing the technique.
Sounds good. Thanks.
Thank you. Great talk. So the checkerboard rendering introduces interframe dependency.
Yeah.
How do you deal with multi-GPU rendering?
So it's one RGBA8 buffer that we have to sync between frames. So on Rainbow Six, we disable all driver syncing, and it's like the driver is not aware of any of the buffers. So we just disable like hardware handling, driver handling from our resources, and we do our syncing ourselves. It's gonna cost, but we pretty much manage to have the scaling on other parts of our rendering, and we still end up syncing that buffer, which is one, let's say, of the few buffers we are syncing. The technique we use for other stuff is pretty much redoing the work each frame on each GPU rather than having the between frame dependency.
Okay. Thank you.
No problem. Other questions? Guess that's it. Cool, thank you. I'll be at the Ubisoft lounge tomorrow at 11 if anyone have additional questions or just want to talk with me. I'll be like on the wrap-up room right now. Thank you, guys.